All right, if we recall from our derivation of the finite element equations, it involves 3 steps. Step 1 is generating the weak form of a differential over a typical element for the ODE, which we are considering. So our original ODE was minus d dx of a du dx plus cu minus f equals 0. And our weak form is the integral from xa to xb of a dw dx du dx plus c wu minus wf dx minus wa du dx evaluated at xa and xb is equal to 0. So step 2 is assuming a form of the approximate solution. As the weak form over an element is equivalent to the differential equation and the material boundary conditions, the appropriate solution that we're assuming only has to satisfy the end conditions, which is our approximation at xa is equal to u1 and our approximation of xb is equal to u2. So our approximation function has to be equal to the value of our solution at our given endpoints. So we're going to assume that the approximate solution is in the form of polynomials because the interpolation theory of numerical analysis can be used to develop approximation functions. Also, polynomials are easy to integrate and differentiate. So there's a few conditions that the approximate solution has to adhere to. The first one is it has to be continuous. So it has to be continuous with an element, and we have to differentiate it as many times as we need. The second one is it has to be a complete polynomial. And third, it has to be an interpolant. Of our primary variable at the nodes. The first two are fairly straightforward. The first condition ensures a non-zero coefficient matrix. The second condition is necessary to capture all possible states, so we're not losing information when we differentiate. The third condition is necessary to enforce continuity of the primary variable at points common to multiple elements. The third point is really key to comprehending the elegance and power of the finite element method. So we're going to start with P1 or linear interpolation. This is your simplest and lowest form. It's the lowest accuracy approximation we can make. So for our current ODE in the weak form, our dependent variable u is only differentiated once. So the minimum order of our approximate solution is linear. So a complete polynomial in the linear form is, of course, C1 plus C2x, or ax plus b. So CE1 and CE2 are constant. So our above expression meets our first two conditions. To meet the third condition, we have to determine C1 and C2 and make sure they satisfy our essential boundary conditions. So if I have an element, I have UE1, UE2, this is XA and XB. I need UH of XA is C1E plus CE2XA, and that has to be equal to U1. And UH of XB is equal to CE1 plus CE2XB, which equals UE2. If I was to put this in matrix form, I would have U1, U2 is equal to 1 times 1 XA, 1 XB times CE1 and CE2. So to solve for CE1 and CE2, we're going to use Cramer's rule. So from Cramer's rule, we're going to determine that CE1 is equal to the determinant of UE1, XA, UE2, XB, divided by the determinant of 1 XA, 1 XB. So CE1 is equal to UE1 XB minus UE2 XA divided by XB minus XA. And CE2 is going to be 1 UE1 UE2 divided by the determinant of 1 XA 1 XB. So CE2 is going to be U2 minus U1 over XB minus XA. And we're going to note that our length of our element by definition is XB minus XA. So I'm going to use some index notation to define a few variables to make this more general and specific as we go forward. We're going to define alpha I to be equal to minus 1 to the j xj, and I'm going to define beta I to be equal minus 1 to the j plus 1, and I'm going to say that xa is equal to x1 and xb is equal to x2. So I and j permeate in a natural order, meaning if I is equal to 1, then j is equal to 2. So if I equals 1, j equals 2, we're going to get alpha 1 is equal to minus 1 squared x2, which of course is just x2. Similarly, we can say the beta 1 is minus 1 cubed, which is minus 1. And then if I equals 2, j equals 1, we're going to have minus 1 to the 1, x1. Should be some e's on here, sorry. Which is equal to minus x1. Then we'd have beta 2 is equal to minus 1 squared, which is 1. So I can write my coefficient CE1 as 1 over h times UE1 xb minus UE2 xa as 1 over he times alpha 1 u1 plus alpha 2 u2, which is equal to alpha I ui over h, and CE2, which is 1 over h times u2 minus u1 as 1 over h times beta 1 u1 plus beta 2 u2, which is beta I ui over h. We're using the alpha I and beta I notation to show the typical form of an interpolation function. And what we're going to do now is we're going to substitute C1 and C2 back into our original approximation solution. So we had UH is equal to C1 plus C2x. So UH, our approximate solution, is going to be 1 over h times alpha 1 u1 plus alpha 2 u2 plus beta 1 u1 plus beta 2 u2 times x and we're going to lump everything together based on our u's. So we're going to have 1 over h alpha 1 plus beta 1 x times u1 plus alpha 2 plus beta 2 x times u2, which is going to be equal to psi 1 of x u1 plus psi 2 of x u2, where psi 1 is equal to alpha 1 plus beta 1 x and this is also going to equal the sum of j equals 1 to n of psi j of x uj. So psi 1 is alpha 1 beta 1 x, which is equal over h, which is equal to xb minus xa, xb over x minus xb minus xa, and psi 2 is 1 over h times alpha 2 plus beta 2x, which is x minus xa over xb minus xa. So these are your linear finite element approximation functions. They have some, so the function psi has some interesting properties. Let's look at the values of our size at XA and XB. So at XA, we have U1 is equal to UH of XA, which is psi 1 of XA U1 plus psi 2 of XA U2. This implies that psi 1 of XA is equal to 1 and psi 2 of XA is equal to 0, which is indeed true. Similarly, at XB, we have U2 is equal to UH of XB, which is psi 1 of XB U1 plus psi 2 of XB U2. So we get that psi 1 of XB is equal to 0 and psi 2 of XB is equal to 1. Why do I care about this? Because this tells me that psi of x is 1 at the ith node and 0 at any other node. This is an interpolation property, which is the final requirement of our approximate solution. So psi is called your interpolation functions. Another property of psi is that they sum to unity. So these right here are your linear interpolation functions. They're important. They're one of the few equations that you should actually memorize for this course. So since they sum to unity, what am I saying? I'm saying that if I have an element, I have node 1 and I have node 2. This black line is psi 1. It has a value of 1. We'll make the green line psi 2, and it has a value of 1 on this side. So the last thing we need to look at is what does the linear finite element approximation look like visually? So I'm going to draw my curve. This is our function u of x. We have point 1 and point 2. So here's my XA and XB. This also gives us points U1 and U2. We have this line, which is UE1 psi 1. We have this line, which I drew really bad, which is UE2 psi 2. And then we have our last line, which is in green, which is our approximate solution, which is C1 plus C2 x, which is U1 psi 1 of x plus U2 psi 2 of x. Well, this is great. We have an approximate function for a solution that's valid over an element. However, it's defined in terms of the location of that element. So what I'm going to do to make things more generic is we are going to define a coordinate system that is local to the individual elements. Instead of using the global coordinate system of where these elements are, I'm going to define a new coordinate system where at one end is fixed at node 1, and I want to write this in terms of x bar, and I'm going to define this system as x bar is equal to x minus xa. So this is local, global, and what do I get? Well, I get that psi e1 of x bar is 1 minus x bar over h, and psi e2 is x bar over h. You're going to be doing this in your homework, but as a quick aside, psi 1 was equal to xb minus x over xb minus xa. I'm going to make the substitution that x bar, I'm going to make my x bar substitution. So I'm going to note that if x equals xb, x bar is equal to xb minus xa. If x is equal to xa, x bar is equal to xa minus xa. So I want to get xb minus x bar minus x bar plus xa over xb minus xa, which is going to give me xb minus xa minus x bar over xb minus xa, which is 1 minus x bar over h. All right. I'm just making a simple coordinate substitution. Next, we're going to look at quadratic interpolation. That will be our next video. It's very similar to linear, but it's quadratic, so it's a little more involved.